Swayam Prabha. Digital India. Educated India.
Welcome back. So, we will continue the discussion where we stopped in the last class is the optimization of these gas turbine units. Now, we will see the different side of a combustion. Now, because one of the key component is, as we said, is the combustion, one can see a multi-scale view of combustion, which will give you an idea that starting from this is our level where you see the furnace application in an industry, that is an one scale which is a large scale application of combustion where the boiler and all these furnaces they are used. From there the why we say the multi scale, because the here scale is always higher than 10 meters and or so, but when you look at in the some other aspect where the swelling flames they are interacting, so this is a scale. So, it is a change of some scale between this application to this application. Now, you move to the laboratory levels scale, that means these are some of these flames which are there, the scale is 0.1 to 1 meter. So, immediately there is a change of a order of magnitude, and when you look at this particular zone in zoomed in, this is how you look at the reaction zone, and we call it a reaction zone. As we go on having our discussion on different kind of flames and such like that, we will see how these reaction zones and their characteristics and all these, but one at this moment can see that the scale of reaction zones in. So, there is a from this to this there is a change of quite a bit of order. Now, within the reaction zone you can have this kind of a small particles which are called soot particles, and I mean essentially when you look at the applications of that, this is what the black particles which comes out of your automobiles, from industrial chimneys and other applications where the black smoke kind of things comes out because of your combusting unit, and these soot particles their length is of this. So, there is a huge change in order of the length scale. So, and finally when you come down to the molecular level, that is the scale where actually reactions and other things takes place. So, if you collate everything together, you can see starting from a molecular level to this furnace kind of applications, there is a different kind of range which are associated. It depends on the particular applications that what kind of range one has to deal with it, but if you couple everything together, you can think about this is a really a multi-scale multi-physics kind of problem. So, now again coming back to some of the example of the gas turbine units. So, this is an gas turbine night cut section of a gas turbine unit. So, why we keep on coming back to this gas turbine units, because this is one of the crucial technologies. There are so many components, so many units, they are connected together, and one can imagine that engine is the only concerned element that actually allows that big airplane to fly. So, you can see these are the compressor, these are the turbine components, and here you sitting the combustor. So, this is also sort of associated with a multi-scale phenomena, because when the flow pass through the compressor, this has a different scale and it enters to the combustion chamber with a different scale where the reaction goes on. So, reactions are taking place at a different scale, fuel is injected. If it is a liquid fuel, then there is that brings in different kind of combustion technologies, and the scales, evaporation, and all these things, and finally it goes out to the turbine and all these things. So, technologies wise this is quite crucial. Now, when you come to a individual component of combustion chamber, one can see these are the some schematic of the combustion chambers. This is an combustion chamber with the annular distributed burner. So, essentially along this there the burners are situated, one can see this, and these are annular sections, and each burner has injector with this kind of configuration. So, each of these individual burners one can see, because these are the cut section which are shown for individual burner, and one can see that this is so complicated. I mean, one is this is sort of an global picture, these are more or less like an micro level picture in that sense, because individual burners which are located around this periphery, there are so many, and that is why you get so much of power, but at the same time when you look at that individual component, they are so complex. Now, that will this one will tell you or give you an idea about the kind of complication. So, this is again an image which is adapted from the internet, that individual cut section of a combustor, of a gas turbine combustor, where you see these are the swell vents through which the air comes in and it get the swelling energy, and here the liquids, and this particle shows that there is a liquid fuel which is injected and a kind of reactions, and then through the you have a secondary tertiary injections. These are the holes which are used. There are multiple purposes of using those holes, because it gives you an advantage of mixing also, so that the temperature distribution at the end becomes quite important, so that the pattern factor reduces, which is one of the desired aspect. At the same time, it allows to cool these surfaces of the combustor wall surfaces, and thirdly, because of this uniform temperature distribution, your emission also reduces. So, there are multiple aspects, but what is important here? So, if you look at this combustion process, there are so many complex things which are actually taking place. Now, what are the problems then? So, you can see this is one of the this kind of combustor unit, where you have a primary air comes in, then you inject the fuel where the combustion takes place. There is around the periphery you have all secondary tertiary holes. So, there are different impact of these holes through which the cooling air are injected, and finally, this combustion product or the hot product goes to turbine. Now, what is important here? Because this particular component, so beforehand for a GT unit you have a compressor feed to combustion chamber feed to turbine. So, you can pumping any amount of, so whole idea of this combustion is that you convert your chemical energy to the thermal energy. So, one may wish to pump in more and more air and fuel, so that you have more combustion and you get more energy, but there are restrictions to that, because it is not only that your combustor material or the combustor liner, they have to withstand those temperature. At the same time, this hot product which are going to the turbine. So, turbine blade has certain limit. So, blade temperature limits the design, because the blade has a particular material and the material has certain limit to withstand the temperature. So, essentially for a GT unit, all these designs come from the downstream component like turbine. Turbine material or the blade material actually dictates what could be the possible maximum temperature, so that T max which is possible. So, this possible temperature will be kind of maintained through the combustor. So, this will dictate what could be the hot product that is entering there. So, that means it is not that I would have a combustor and I can burn as much of as fuel and I can produce energy, because that has some restriction. and the restriction in the terms that the turbines would not be able to withstand that. So, one may look at what are the engineering problem here. So, if I am a designer, my whole point should be turbine should not burn, that means turbine blades should not burn. So, that is one of the important point. Then at the same time, because this will dictate what could be the possible maximum temperature, but at the same time I would like to have the efficiency. Typically any gas turbine combustor, the efficiency lies around roughly 99%. So, there is not too much of loss. The combustor is one of the component in a GT unit where you have quite efficient system. And then third is that emission. So, this should be low. So, that means my CO and NOx should be low. So, that means I am trying to again optimize the whole system. I do not want to increase my temperature to a limit which will lead to a catastrophic failure of the turbine elements. At the same time, I want my efficiency to be close to 100%. If not, it still remains at 99% efficient, and the emission, which is another stringent norm that one has to follow. That means the emission norms should be fulfilled. So, that brings to an important question: how do we optimize to reach all these goals at the same time? That means there are certain things which are counter intuitive, because if you go to reduce one of these element, other may go up or other may go down. If you so, it is again an trade off, especially in terms of emission, because these guys are also dependent on temperature. Too high temperature, the NOx will go up and the CO will come down. So, it just like an, if one plot the temperature axis and NOx and CO, too high temperature this will go up and too high temperature this will come down, but if you go to too low temperature, CO will go up, NOx will be low. So, that means even in the emission products there are different characteristics. So, it is a trade off, one need to operate a system in a bandwidth limit of temperature. So, you sort of compromise or on these emissions, and at the same time this compromise would have impact on the turbine blades, but at the same time if you operate between certain limits, your efficiency may not be that high. So, we talk about different kind of combustion, their applications, the impact on the downstream component of different units and all these. There is a simple example of backward facing step where you have propane and air as a premix gas which is injected at a temperature like this, and this is the combustion product, and this goes to basically exit or the exhaust. What we can from the image, one can see this combustion is a stable, I mean obviously this is a turbulent combustion, this is no more very calm nice looking combustion like your candle burning. So, it is a stable combustion. Does that mean that means we can have also unstable combustion? Yes, we do. I mean even for this particular case, as long as you are sending this mixture which is burning here, so you get some sort of a stable combustion. So, mixture is coming in, it keeps on burning, you get everything stable. You change some of the parameter at the upstream, maybe you modulate the this upcoming mixture, or you modulate the fuel flow rate or air flow rate, any of these things. So, any of these small change in the operating condition, it would lead to an unstable condition, and rather one can say that it triggers the instability, and you can see there is a huge difference in the flame structure. So, previously it was a nice stable structure, now you see this is quite unstable structure. And how it happens? It happens because somebody might have tickled the upstream condition. So, and these are one has to understand, because these are having, I mean, combustion is nothing but your some reactants and oxidizers. These are multi-species systems which are convected due to underlying fluid mechanics. So, there are certain changes in the fluid dynamical behavior, things would lead to this kind of situation. And what happens there, that you have some unsteady flow rate. So, that means, as I said, it is a dynamical system coupled with so many different scales, different phenomena, not only fluid mechanics, reactions, heat transfer, mixings, everything. So, there is an unsteady flow rate, and the unsteady flow rate which will have large vortices. So, once you have large vortices, that means any turbulent flow will have large vortices, and we will see later on when we will talk about the turbulence how these large vortices actually behave, their characteristics, scales, all sort of different things, and that will lead to some sort of an unsteady heat release. That means, see, when you talk about these vortices, they are actually carrying those species, or rather reacting species, and reacting species, they are also exposed to this underlying fluid dynamical behavior, and that will lead to unsteady heat release, which will generate some sort of an acoustic shock. Once that happens, this is again is going to couple it back. So, that makes the whole system literally unstable, and once you have this unstable system, so you may have some consequence, and these are the some of the images of those things where you can see there is a big crack on the combustor valve. You see what happens to the swell burners, some damage to the dump plane and the combustor valves. So, this kind of instabilities has huge impact on the operating conditions as well as on the materials point of view. So, one can think about the turbulent combustion is a stable one as long as they do not exhibit any significant instability. So, that is how one can. So, what is important? Important is that then one has to look at things through CFD, which is quite essential, but not yet able to do its job because of so many things. You have kinetics, because this is important for any combustion which is connected with turbulence. Then depending on the applications, you have a radiative effect, you have huge heat transfer, structural impact. So, it is not like that experiments are always expensive and something like that, but sometimes CFD is also quite difficult for problem like turbulent combustion, because you have so many connected flow physics, and so still one can think about experiment is really necessary, because there are so many nonlinear phenomena that takes place in a combustion. It could have an explosion, or when the combustion is taking place there could be local quenching, that could be another possibility, or there are oscillations and limit cycles, and all the issues, the backbone of that is the turbulent. So, this is what remains a major problem. So, that means if you see things happening when you talk about the turbulent combustion, and the combustion itself is complicated, top of that when you are kind of dealing with a turbulent system, that creates another level of problem, or that remains a huge problem. Now, to just give you a glimpse of what turbulent flow field looks like, though we will discuss these things in details as we move along with our lectures. This is in a box isotropic turbulence, that means it is sort of an homogeneous. you can see the small scale vertical structure. These are small scale structures, vertical structures, and this kind of structures along with the large scale structure, they do participate in a reacting system. So, what it does, one can see a different images. This is a macroscopic view, and then if you zoom in, you can see different view, zoom in more, you zoom in more. So, essentially in a turbulent structure, idea is that as you keep on zooming in, you will look to see a different kind of structure at different scales, and that is what it is a large scale L. This is L and lambda, 50 eta lambda, this eta lambda, these are some sort of a scales which are used in turbulence, and we will discuss about these things, but these are the, when you go to lambda or eta, these are the limits of small scale and defined by different scientists. This is stellar length scale, this is Kolmogorov length scale, and idea is that as you, this is an isotropic box, and if you zoom in these pictures, you can see which is quite unsteady in nature. This is truly 3-dimensional, and they do have lot of small scale structures and all this. So, idea is that, or the question is that, can we really compute this? But it requires sophisticated modeling technique, so one can handle this kind of situation. So, what we do usually, and what are the sort of impact of doing that, and once you do that, usually what we do to model the turbulence, it is a very much quite common in industry, because they need to get a solution in quick time. So, they average the turbulence, but as you have seen, the turbulence itself is truly unsteady and 3-dimensional in nature. It requires really a 3D computation, or I would say 3D detailed computation, so which can resolve all the scales. So, or one can think about scale resolving computation, but if you talk about scale resolving computation, that is quite expensive. So, what people do, sometimes in academia, sometimes I mean mostly in industry, they use mostly RANs, and you get the solution in quick turnaround time. So, that is what we do, the averaging. And what kind of averaging you do? One of couple of them are, if you look at the gas turbine, you averaging with time because of the unsteady flow, and when you go to piston engines, you go by the cycles, how many cycles, and do the cycles averaging. But if one has to answer this question, is the averaging is a good idea? Obviously not, but this has some reasonable compromise, because by doing this one can get solution in quick time. So, what if you put things together, combustion is a complex interaction of so many different processes. There are physical processes which are like fluid dynamics issues, heat mass transfer issues, then it is associated with chemical processes like your chemical kinetics, thermodynamics, conversion of the chemical energy to thermal energy, and not only that, any real life applications of this combustion, they also involve lot of applied sciences. So, if one has to look at it in a combustion process, what it happens, so it can be governed by few fundamental governing laws like energy, mass, momentum. So, these are the physical processes which are involved in combustion and they are transported. So, mass, momentum, energy. So, top of that you have some conduction of thermal energy, diffusion of the chemical species, because without that your reaction cannot take place. So, it because of the interaction of the different species at the molecular level, that would allow to reaction to take place and evolve, and then flow of the gases all follow from the release of chemical energy into the exothermic reaction. So, the things which are more or mostly relevant in combustion, one is very important is the thermodynamics, transport phenomena. Transport phenomena means your momentum transport, species transport, mass transport, kinetics, and some of these one can summarize. So, if you first look at how the thermodynamics is going to act to that, you define different things like equilibrium, heat of formation, heat of reaction, properties of gases, stoichiometric, flame temperature. These are the things one would be able to estimate through the thermodynamical analysis. Now, once you bring in heat and mass transfer, so you have heat transfer due to convection, conduction or radiation, any of these mode, and that depending on the problem you deal with, you have this heat transfer and that to be taken into account, and then mass transfer obviously, because you are transporting different species which are involved in this particular process, and they actually do take part in this kind of heat and mass transfer. And finally, your fluid dynamic features, these are also very important, whether you could have a laminar flow or turbulent flow, because this makes lot of difference. Already you have seen just the glimpse of this turbulent combustion. I mean, if you think about your candle burning, this is nothing but your laminar flows and laminar burning. So, it is so calm, smooth, there is no apparently issues which would be a immediately catastrophic, but when you talk about turbulent reacting system, they could be. Then there are inertia, viscosity, all these transport properties, and combustion aerodynamics. Now, when you come to the kinetics, this is nothing but the application of thermodynamics to the reacting systems, which will give you an equilibrium composition of the combustion product. That means, when multiple species they are reacting to each other, one can estimate what would be the equilibrium compositions. So, that means it just like an collisions between different molecules and they reach to a certain equilibrium, and at the same time, because of that, the maximum temperature corresponding to these kind of compositions, which will so called adiabatic flame temperature, or rather this is a theoretical estimate of flame temperature for a given species or given reacting system, or for a particular fuel and the oxidizer. If you change the fuel, this theoretical limit or estimate actually. So, thermodynamics talks about these things, but at the same time one has to also note that thermodynamics alone is not capable of telling whether the system will reach to equilibrium or not. So, that is another issue. That means, thermodynamics can give you estimate of these things, limits, equilibrium compositions and all these things, but it does not tell you that if the time scale of chemical reactions involved in the combustion process, which are comparable to the time scale of the physical process, that means the diffusion, fluid flow taking place simultaneously. So, system may never reach to equilibrium. That means, immediately your other aspect of the things comes into the picture, like there is a convection taking place due to fluid dynamic behavior, and that allows to have diffusion to take place, and the time scales are quite different. Now, the typically in any reacting system, the time scale of chemical reaction is quite different from this kind of other time scale. So, that is where another important issue which comes into the picture, how one has to deal with these different time scales. So, one has to calculate the rate of chemical reactions which are involved in this combustion. So, some of the materials are also collected from, these are the not all, but these are the primary sources of combustion research literature. One may look at this because there every time there is a issue out there, one can see different aspects which are discussed. These are the sort of primary sources one can look at and then get more insight about recent advancement and other details. So, I will stop here and take it up in the subsequent lecture. Thank you.